Thank you, Jay. Good afternoon, ladies and gentlemen. It's an honor to be here. Before I start, I would like to thank 동부하이텍 for organizing this meaningful and important event. Thanks for inviting me over to give you some of our perspective on what the age of smart convergence. Thank you, Jay. Good afternoon, ladies and gentlemen. It's an honor to be here. Before I start, I would like to thank 동부하이텍 for organizing this meaningful and important event. Thanks for inviting me over to give you some of our perspective on what the age of smart convergence equipment manufacture. Our products cover almost every aspect of modern days communication networks. Therefore, we have some first-hand knowledge about the technologies we need to build the networks for today and tomorrow. Among all these technologies, we found power to be a very critical element. Therefore, in my presentation today, besides some general discussion about us, ZTE, and our views on smart convergence, my presentation will be focused on the discussion of the power IC design opportunities. My presentation will be divided into three parts. First of all, I will give you some a background about us and our perspective on what the age of smart convergence looks like. Second and third, I will talk about the opportunities in the communication IC design and power IC design, because we think these two areas are the most important areas in the age of smart convergence. This is a table of the products we make. There are quite a few columns here, but generally speaking, we have three major core businesses. We have terminal business, which covers the cell phones, smartphones, data cards, and the tablets. We have a wireless business. It's all about base stations. So we make base stations for all kinds of cellular standards. And we also have a wireline business. It actually consists of a few columns here, including the fixed access and bearer network. It's all about the optical networks, ADSL, switch networks, etc. We also have a small, nascent, but rapidly growing business in the cloud computing. On top of all these hardware, we also provide services to our clients. If you have been following the rankings of the cell phone manufacturers in the world, you probably have noticed that ZTE has been steadily rising in this ranking. We're now among the top 4 in terms of the terminal shipment. And our handset overall sales grew by 50% in 2011. Especially in the smartphone area, our growth rate was ranked number 1. As of Q1 this year, we remained at number 4 in terms of the terminal shipments. In 2012, our focus is on the smartphone. We have over 10 years of handset design experience, nearly 400 professional design experts. As of Q2, we are already one of the top 5 smartphone manufacturers in the world. And the cell phone, Blade 880, which is this one in my hand, this was the most popular mid to low-end smartphone in China in 2011. In the wireless business, we have seen very steady growth for 2G and 3G. We are currently number 1 in the TDD market and CDMA market. TDD mainly is the Chinese homegrown standard, which is TD-SCDMA. We are among the top 3 in the UMTS market as well as the GSM market. In the upcoming 4G generation, we already helped our customers deploy 30 LTE commercial networks globally. We are currently supplying the trial networks for over 100 operators, and 8 networks have been commercially launched. As you can see, these telecom carrier names, they're well known throughout the world. In the wireline business, we are also playing a very important role here. We are number 1 in OLT, PON, DSL aggregation product, and we're among the top 3 of IP, Ethernet, and optical network. As you can see, in terms of the communication, we are really a very one of the premier players in the world. This picture shows our views on what the data-centric communication networks look like in this age of smart convergence. We have terminals. We have terminals which generate the data, and the base stations, gateway, and switch network that relay the data. And we have the cloud that process the data. So after the cloud, so basically among all the terminals, the smartphone, the cell phone, especially the smartphone, draws the most of the attention because just the sheer volume of the smartphone terminals in the world, and also the size of the business is just so large. Also because the technological sophistication in the smartphone probably represents the state of the art. The other term, the smartphone talks to, the smartphone generates data by either talking or taking a picture or shooting a video, and then the data is transmitted to a base station through the cellular wireless technologies such as WCDMA or LTE, and it can also connect to the internet by the home gateway through Wi-Fi. The other terminals that can generate data are sensors. As the sensors are getting more and more ubiquitous, they can indeed generate a lot of data. For example, the biometric sensors in our watch, or the sensors in a thermostat. They can be, this data can be connected to the internet either through our home gateway or our smartphone as a mobile gateway. The other terminals include the PCs, the notebooks, or the TVs. The dashed line here, basically, on the left, the items on the left are the things we don't do, and on the right are all the equipment that we produce. You can see that we are indeed a very important player in this area. And when the data are transferred to the switch network, they are bundled together and transferred into the cloud through a barrier network. As you can see, because of the data aggregation here, the bandwidth requirement is much larger, in the range of hundreds, 100G. Inside the cloud, the data are processed by the servers, thousands of servers working in parallel, and the processed data is then fed back through the same network until they're ultimately consumed by the terminals. As you can see in this picture, communication is everywhere. No matter the communications between the cell phone and the base station, or the communication between the switch network and the cloud. Communication is really one of the most important technologies for the age of smart convergence. The challenge mainly comes from the increased data rate, more bandwidth. Therefore, we see a lot of opportunities here. The second important area to look at is the power, certainly. One thing for terminals, it's quite obvious because most of the terminals are not plugged into the walls. They have to work with batteries with very limited capacity or no battery at all. Therefore, it's very important to make sure that they can work under a very stringent and sustainable power budget. On the other end of the equation, in the cloud, we have thousands of servers in the data center, and each server can, if you add their power up, it can be a very huge number. How to deliver the power to the data center can be a critical issue, which I will talk about in the following slides. So the communication and power management are really the key analog technology enablers we see in the era of smart convergence. In the communication, the challenge will mainly come from the requirement for higher speed, more bandwidth, and especially in the cellular communication world, we need to support multimode, such as 2G, 3G, and 4G altogether, and multi-band. And on top of all these, we need to be low power. And in the realm of power management, we need more power, more efficient power delivery, less standby power, better battery management methods, and for the system, the cloud, we need higher power density. So now let me talk a little bit about the analog opportunities for communication IC design. In the communication, three areas seem most interesting to us. The first and foremost is certainly RF. We find the transceiver design to be very challenging in the upcoming future, especially in the cellular transceiver design. The reason I will talk about in the next few slides. The transceiver design for connectivity IC could be challenging as well, but we think the cellular transceiver design will present the most challenges. There are a few ADC designs that seems to be very challenging and present some opportunities there. One thing is also related to the increased data speed in the cellular network. It requires analog baseband ADC with much higher speed, but with very low power budget. And in the 100G network, we need ultra high speed ADCs in the range of 50 gig samples per second. And the other important area is SerDes. The SerDes I'm talking about here is actually the analog technologies behind all the high-speed serial interface. In terms of application, it can be divided into backplane, optical, and interchip connect. Let me talk about the RF design first. This picture shows the communications around the smartphone. On the left, the smartphone can talk to the base station through the cellular networks either 3G or 4G networks. And on the right, it can talk to a lot of other devices, such as a wireless router through Wi-Fi. This can usually provide more bandwidth. It can also talk to sensors, for example, through some low power wireless standards such as Bluetooth. And it can also talk to a satellite up in the sky through GPS protocols to provide the global positioning capability. Inside the RF transceiver, we have a receiving path and a transmitting path. In the receiver path, the transceiver will basically use a linear low noise amplifier to precondition the RF signal. Then there's a mixer that can demodulate the RF signal into baseband. The baseband signal is filtered and then digitized by the ADC in the analog baseband, and then it's sent to the communication processor. In the other direction, when the cell phone needs to send out some information, the communication processor sends the signal, the digital information into the baseband, analog baseband, and then the digital information is converted into analog, and then it's modulated by the carrier in the transceiver before it's sent out to the power amp. The transceiver structure in the connectivity IC is similar, but usually the transceiver is integrated with the baseband, the digital baseband. And the communication processor mainly does all the channel coding and decoding according to various cellular standards. And the application processor is basically the brain of the smartphone. So we see a lot of ICs here. Their interchip connection is usually based on some kind of SerDes-based technologies, such as DGRF or some other kind of MIPI standards. Besides all these, we have the PMIC, which is a power management IC that provides the power to all the components in the smartphone. So these are some key requirements for a cellular RF transceiver. First and foremost, it has to be multi-mode. The reason is quite simple. Because of the rapid evolvement of the cellular technologies, we have 2G, 3G, 4G networks coexisting at the same time, probably throughout the world. And another thing is people are getting more and more mobile. So today you may stand in an environment with only 2G network, but tomorrow you may be downloading your movies through an LTE advanced network in a different country. So therefore, your smartphone has to be able to support various cellular standards at the same time. And the second requirement is multiband. This is related to the fact that the carriers around the world want to have a better utilization of some idle bands. So in the era of LTE advanced, we see that the carrier frequency can go as low as 600 megahertz. So basically the carrier frequency will have a much wider spectrum range in the future. And there are many isolated bands that can be utilized, that will be utilized. But this will certainly present a challenge. The third requirement is the MIMO, multi-input, multi-output. It's a technique that will help to increase the signal-to-noise ratio of the incoming RF signal, and ultimately it will help to the increase of the data rate. The fourth is carrier aggregation. It's a technology used for LTE advanced. Basically, the idea is that for a wideband baseband signal, it can be divided into two narrowband signal, and these two narrowband signal will be modulated separately and later combined again on the other side. The last but not the least, solids. Solids basically means we don't want external SAW filters. The reason is quite simple. Our customers want to reduce their costs. They don't want tens of SAW filters sitting outside of the transceiver. Therefore, this is becoming a more and more standard requirement. This is a typical RF cellular transceiver block diagram. On the top, it's the receiving path. This is a low noise amplifier, the mixer, which demodulates the RF signal into baseband. And then the filter, the ADC that digitize the baseband signal. On the in the other direction, the signal will be converted into analog by DAC, and then it's modulated by the mixer as well. Because of the requirement for multi-mode, multiband, there could be quite a few channels, both on the receiving end and transmitting end. All the other blocks are sort of the supporting blocks that can make sure that these channels are working properly. So what are the major design challenges in the RF transceiver design? The first, we find the integration of 2G into 3G, 4G network transceiver to be quite challenging. As some of you may be aware of, 2G, which is GSM or Edge technology, it's fundamentally different from the 3G technologies. So the design mindset and the techniques behind the transceivers for 2G are quite different from 3G, 4G. So people who are good at 2G may not be good at 3G and 4G. And there are not many suppliers that can do a good job in integrating 2G together with 3G and 4G transceivers. The second challenge is how to make your design very area and power efficient. As we can see in the previous slide, the number of channels just gets more and more. If you want to maintain the scale of your design, you have to figure out a way to share the channels and to reconfigure the channels. The third is the bandwidth. That's obvious because the data rate increase, the channel bandwidths have to go up as well. And the fourth is the carrier frequency range I'm talking about. This could be a headache for the VCO designers. The solids is a challenge as always. And last but not least, the spur control. This is actually, the spur is usually how well you can control the spurs usually differentiate a good RF transceiver provider versus a mediocre one. Another important opportunity in the communication area is also related to the cellular transceiver, RF transceiver. This is which is the baseband ADC. As you can see on the picture on the right, the data speed has increased dramatically from 2G era into 4G era. In old days, the people they are content with data rate in the range of 100 kilobits per second. But when 3G comes, when we see an explosive growth of smartphones, the data rate requirement also quickly increased from around 300 kilobits per second, almost all the way to 30 megabits per second. In the next generation network, the data rate will keep going up all the way to probably a couple of hundreds megabits per second. So what's this mean for ADC design? First, higher data rate needs higher bandwidth. Now we're talking about the ADC to support the signal bandwidth of 20 megahertz or more, the sampling rate about 40 megabits per second. Second, because we are moving, in order to increase the data rate, we're utilizing some modulation scheme with better spectral efficiency, such as 64 QAM. This would require a better resolution on the ADC. So before we use 10 bits, nowadays 12 bits, we need 12 bits or more. But if you just look at the bandwidth and the resolution, it's not that difficult. The key here is really the low power. Because it's in a terminal, we have to be able to design it under a very low power budget. Therefore, this is becoming a very challenging design for a lot of suppliers. So far, the solutions we've seen are mostly based on continuous delta sigma ADC architecture or pipeline architecture, some innovative pipeline structure. Another interesting area for ADC is actually in the wireline network. The picture on the top is a top-level picture of the 100G network. In this network, there is a line module. Inside this line module, on the receiver path, there are four very ultra-high-speed ADCs that are required. The basic idea is based on the WDM technology. WDM means wavelength division multiplexing. So the kind of high-capacity waveform, it has four phases in the form of optical signal, in the form of light, and then the photodiode will convert that light into electrical signal. And electrical signal will then be digitized by these ADCs. So the requirement for these ADCs are sampling rate in the range of 50 gig samples per second or more, resolution in the range of at least 6-bit ENOP, so usually people design it with 8 bits. Bandwidth needs to be 15 gigahertz or more. So far, there are only a few countable few suppliers that can do this in the world now. The solutions we've seen so far are either based on SAR, with hundreds of SAR ADCs in parallel, or some kind of innovative pipeline structure. Important thing to notice here is that these ADCs are usually required to be integrated with the SoC. So it's important to design them in 65 nanometer or below, because that's where the SoC's process are going to. The last slide in the communication area is SerDes. As I mentioned earlier, SerDes I'm talking about here is the fundamental analog technologies behind all the high-speed serial interfaces. So the key design technology there is really the clock data recovery and the design of PLL. This is a diagram that lists all the standards. I don't have time. I don't want to delve into the details about what these standards are, but their basic technologies are similar. In terms of application, in the optical world, we're seeing the speed moving from 10G to 20G. In the backplane application, it's moving from 6G to 10G. On the interchip connect, it's currently at 5G, but since on the interchip connect, we need SerDes as an IP, so they need to be low power, and they need to be designed in small geometry and migrate along with the advancement of the technology node. So that's a brief discussion about the opportunities in the communication IC design. Now let's take a look at the opportunities in the power IC design. The picture on the right basically shows the trend of the energy consumption from the traditional world versus the energy consumption from the infotech industry. As we all know, with the growth of worldwide population and the increase of living standard, the energy consumption, total energy consumption will go up. But with the help of infotech and some other kind of technology advancement, this curve, the energy efficiency will go up as well. So sometime in the future, this curve will gradually level off. But it's a different story for infotech. As we all know, infotech is all about data, the generation of the data, the delivery of the data, and the consumption of the data. And every stage of the data processing requires power. Therefore, we see, because of the explosive growth of data, the amount of data in the age of smart convergence, we see an explosive growth of the energy consumption from the data as well. Although the efficiency of the energy efficiency of this data processing keeps getting better and better, but the data generation speed is just easily outpacing the efficiency improvement nowadays. And I don't see limit in the data generation inside for now. Therefore, sometime in the future, the total energy consumption from the infotech will surpass the consumption from the traditional sources. Therefore, it's very important to take the power design very seriously for the infotech industry. The analog opportunities for power design can be viewed in terms of its applications. In the terminal side, we have many opportunities in power management or the charging management, and LED backlight or flashlight. I'll give you a few examples in the following slides. On the system side or the side of the servers, the clouds, we see opportunities in AC/DC design and DC/DC designs. So this picture shows the basic idea behind the power management. Basically, in a system, in an SoC, the system usually knows what kind of task load it's performing under. So when the SoC is not required to work in full power, the supply voltage and the clock speed can be lowered to reduce the power. Also, the PVT sensors will tell the SoC what kind of corner or the supply voltage or the temperature that this IC is working under. And with all these informations, SoC can determine the optimum supply and the clock frequency for itself. And then it sends a command to PMU, and then PMU generate the supply and the clock in accordance. So basically, the basic idea behind this is basically the adaptive voltage and frequency control. The PMIC for mobile handsets, we see usually we see these building blocks. Usually it will need DC-DCs. Most of them are bugs. The number of bugs can range somewhere between 2 to 6. The output current can vary from 1 amp to 3 amp. they all need to be adjusted. They cannot be digitally adjusted, which is what DVS means. And sometimes we need a boost DC-DC for LED backlight driver. And then we need LDOs, a lot of them. Usually it's in the range of 10 to 20 channels. And for the supply, for the LDOs that provide the supplies for RF transceivers, it needs to have a very low noise. The noise requirement is really stringent over there. And in many cases, we have the charger integrated in the PMIC. And we're seeing a migration from linear charger into switching charger as the battery size is getting bigger and bigger in the smartphone. And we have a we have a bunch of housekeeping blocks, such as the power and reset and real-time clock. And sometimes some seemingly unrelated, power-unrelated blocks are also integrated in the PMIC, such as audio codec or a USB 5 or touchscreen control. It depends on the applications. So here is a block diagram of a handset PMIC we built for feature phone. It has 2 buck DC-DC with DVS capability and 12 LDOs. It has an integrated charger. Since it was still a feature phone, it's a linear charger. And we have the codec integrated with the audio, with the power amp for audio power amp. And there's a general purpose ADC for all the kind of diagnostic work. And the POR provides a power on down sequence control, real-time clock, I2C interface, and LED motor drive. So you can see that this IC is actually quite complicated. It can be called, I think, a analog SoC. So what are the challenges related to this SoC? The ones we find that are important are in the DC-DC, where the efficiency is really important. The DC-DC needs to have high efficiency both at light load and low load condition, and it needs to have very low standby power, and for the purpose of DVS control, which is supply adjustment, the output needs to be adjusted very quickly and with high resolution. And since we have more than 2 DC-DC switching regulators in the same die, the cross interference could be a real challenge sometimes. And for LDO, the challenge mainly lies in the noise concern and the standby power. The overall efficiency needs to be good, and for many cases, you'll find heat to be a critical challenge. And on top of this, all these, we have to do it with low cost. This is related to our business model. Our customers are pushing us really hard to lower the cost. Another example for the PMIC is the power management IC for set-top box. Here, the requirements are a little bit different. Our input voltage stands at 12 volt. We need at least three bucks for our supplies. 12 volt to 1.2 supplies the voltage for the core, which is usually the SoC in the set-top box, and 5 volt is for accessories, and 1.8 or 1.5 is for DDR. So their current load is in the range of 3 amp or 1.5 amp. And for all the other supplies, we use LDOs, since the load is not that heavy in most cases, in the range of hundreds of milliamp. All the other requirements are similar to what you see in the cell phone PMIC. This is a typical block diagram of the PMIC for set-top box. Again, the challenges here are similar to what you find in the PMIC challenges for a cell phone. The efficiency is always one of our biggest concerns. Heat management is related to efficiency. And here, the standby power has to be maintained very low. It's a requirement by Energy Star. Currently, the whole set-top box needs to limit its power consumption to a level below 0.5 watts when it's in standby. So it's a challenge for both the SoC designers and the designers who supply the power to the SoC. And it has to be low cost. This is a slide talking about the opportunities in the charger design. The picture on the left is a charging profile, a diagram of a lithium battery. The blue line is the battery voltage, and the red line is the charging current. When the battery is deeply discharged, it needs to be charged with very low current, which is called trickle current. And then as the voltage goes up to, let's say, 3 volts, the current can be increased to a much higher level, which allows for much faster charging until the voltage reaches 4.2 volts. When the system gets into a constant voltage mode. Here the output holds at 4.2 volts, and the charging current gradually dwindles down all the way to 0, and then the battery is fully charged. And in this industry, there is a rule called 4 hours rule. Each terminal needs to be fully charged within 4 hours. So based on the size of the battery, different level of the charging currents are required. For example, in a smartphone, the battery is usually less than 2,000 milliamp hour, and the current we need here is usually in the range of 1.5 amp. And for U-Fi, whose battery size is around 3,000, we usually need a charging current in the range of 2.5 amp. For tablets, whose battery is about 7,000, the current needs to be much higher as well, around 4 amps. So these are the devices with this kind of the terminal devices with this kind of battery size are fairly new. That's why the opportunity for charging these devices are quite attractive to us right now. This is a typical application diagram of a switching charger. The technology behind it is actually similar to a traditional linear charger, except that the power is generated by a switching regulator. So in some sense, you can think of it as a switching regulator plus a traditional linear charger. The major design challenges we see here is the loop stability, because the charger has to be able to charge the battery while providing the supply for the terminal SoCs based on all kinds of load conditions. The loop stability, and based on all the load conditions and based on all the various stages of the charging process, the load stability could be a pretty challenging issue to tackle. And the second is again similar to what you find in other power ICs, efficiency and heat management. And sometimes our customers are talking about fast charging, meaning that they prefer the battery to be charged in less than 4 hours. There's some interesting technology here, but I don't have time to delve into the details here. Just for fun, I'm adding another slide here for wireless charging, because this seems to be a very hot topic nowadays. The wireless charge, the basic technology behind wireless charging is similar to the traditional charger, except that the power is delivered here through a wireless coupling technology. The basic idea is the primary side, which is the charging pad, is plugged into the wall, so it always has the power. When it detects a secondary side placed on it, it will start a driver and pumping the AC current into this inductor. And as we all know, AC current will generate a magnetic field, which is coupled into the inductor on the secondary side. And then this field will generate the current, which is then rectified, and the power is provided to the charger. And the charger will take care of everything afterwards. It will take care of the charging profile for this lithium battery. And on top of this, the primary and secondary side needs to know when the charge is needed, and some other information. So there's a communication protocol between the two sides, which are handled by the controllers on both sides. Currently, the wireless charging is pushed by the WPC, Wireless Power Consortium, and the standard is called Qi. If you watch a Chinese Kung Fu movie, you probably know what Qi means. It means, it's a Chinese term for invisible energy. The frequency in concern is 100 kilohertz. The pros is certainly very obvious. It's very convenient, and it's also very cool. I think for most of the young users. But also the con is quite obvious as well. The efficiency, the charging current are not as good as the traditional charger. And you certainly want, when your current is deeply discharged, you certainly can't make a phone call with the wireless charging. So convenience could also be an issue here. So this is interesting technology, but it's still hard to say whether it will take off or not. Last, let me present a few slides on on powering the data center. The picture on the left is what a typical data center looks like. So it's a bunch of servers on the racks standing together. And the picture on the right are the data centers operated by China Mobile. It's all across China. And as we all know, the data center is driven by the data. We are in the era of big data, and smart convergence drives the growth of data centers. And these data centers can consume quite a huge amount of power. For example, most of these servers inside the data center consumes about 1 to 20 kilowatts per rack. Sometimes people are pushing it all the way to 25 or even 30 kilowatts per rack. Let's say they are operating at 20 kilowatts per rack. So that means 5,000 racks will consume 100 megawatt, which is a typical power output level of a traditional power plant, such as a coal or hydraulic. So powering data center is really becoming a more and more challenging issue. This slide, the picture on the right, is copied from the APC white paper. It shows that the space usage the space utilizing rate for the servers under different kind of power level. For example, when the server rack consumes about 10 kilowatt, it means you can only have 40% of the total space to deploy the IT equipment. All the other area will be for the air conditioning equipment or left empty just to manage the heat problem. And for every watt delivered to the IT equipment, the same amount of wattage is actually needed for air conditioning. So low power design is really important here. The low power design for the server processor has been a very hot research area nowadays. And on top of this, we can see that size does matter for the power delivery modules. Our customers want us to make our power modules smaller and smaller, which means more and more power density. And therefore, efficiency is important both for heat and cost concerns. Some people are proposing that the components work under higher temperature, which can save the cost on the air conditioning, but still there's some long way to go in that direction. Because of the need for smaller and smaller power delivery module, our customers are talking about a module looks like this, a DC-DC converter, which is monolithic with 20 amp technology, with 20 amp capability. As Steve pointed out earlier this morning, the current state of art is 10 amp, but our customers are wanting 20 amp. So maybe we can do some sort of do it with some sort of SIP, but this is bigger current capability is definitely the direction. And we also need to have inductors and capacitors and some other components integrated in this module. And they need to have very small form factor, and the efficiency and the thermal resistance of this package needs to be very good. And the reliability is important as well. So these are the, because of the limit of the time, I just basically roughly go through the opportunities we see. Anyway, we find in the age of smart convergence, there are indeed many exciting analog opportunities, especially in the communication and power designs. I think we can tackle these challenges by innovating in the design as well as making advancement in the processing technologies. Last but not least, as you can see throughout my presentation, our company ZTE has been and will continue to be one of the most prominent players in this upcoming age of smart convergence. Thank you very much.